for critical. Oh, sorry. What is this? Okay, continue.
Sorry, that was my bad. So continue.
Yeah, no worries. Okay. Right. So we're talking about critical points of this Willmore energy that are conformally equivalent to the input. So we want the target surface to preserve the metric of the initial one up to local scalings. So meaning that the local neighborhoods of corresponding points in the initial and target surface should be scaled versions of each other. Yeah, this is what this shows. So if we try to formalize it a bit, what we could say is that the surfaces, the starting and the target one or the final one should be conformally equivalent. So, or equivalently that their induced metrics belong to the so-called same conformal class. So, sorry guys, 1 second. Yeah, well, if they, somebody might walk in and I'll have to tell them that I'm in a talk, so yeah. Okay, so right, classes of metrics. So a metric, as probably all of you might know, is this symmetric positive definite bilinear form. So we have these tangent vectors x and y on the manifold, and we have this choice of imposing a metric. This can be thought of as an inner product between these tangent vectors, and the induced metric from a surface F is defined via the push forward of these vectors, x and y, via F. So one takes the x and y tangent vectors, then it pushes them to R3 by using this Jacobian, and then you get these 3D vectors, df of x and df of y, and then you take the standard inner product in R3, and that's your metric on the induced metric on your surface. So then we can define conformal classes of that. So that says that one metric is a local scaling of the other according to some positive conformal factor u at every point. And this u, it doesn't have to be constant for the entire surface, so it can be a function on your manifold that sort of varies smoothly. And what this says is that we, if the surface that we start from and the final one have metrics, induced metrics that belong to the same conformal class, then we say they're conformally equivalent. And in fact, there's another way of looking at conformal equivalence by looking at the so-called almost complex structures from differential geometry. So these are these fields of endomorphisms on the surface, meaning that at every point you assign a smoothly varying linear transformation on the tangent plane. And so there's the special endomorphism field J, which is essentially a 90-degree rotation. It squares to minus identity, and it's depending on the metric. So it turns out that every conformal class corresponds to a unique structure J. So these immersions will be conformally equivalent if and only if they induce the identical complex structures. I'm not going to need this for this talk. This is just another fact. So from a practical point of view, it's nice to add the conformal constraint to energy optimization because it ensures that the meshing quality is preserved. So it happens a lot that when you optimize for some energy and you do some flow, then you get the meshing quality to degenerate, and in particular, so for nonlinear things like Willmore. But because we're using these conformal transformations, which locally preserve angles, then we can guarantee that equilateral triangles stay equilateral at the end if we apply the conformal constraint. And of course, this has been known in graphics because conformal transformations have been used for parametrizations a lot, and people like them because exactly they preserve this element quality, and also as a consequence, they distort the textures less. Okay, and so one final thing I wanted to mention is that there's an interesting connection between this problem of constrained Willmore surfaces and spline modeling. So we have, of course, this polynomial splines that everybody uses in graphics, but in fact, those were inspired by physical splines. So those were these thin rods that made of wood or some other inextensible material, and they were pinned down by hand by the designer. And what the mathematical model for this is exactly a curve minimizing this bending Willmore energy in 1D under point constraints and also under a constraint of local isometry to preserve the rod length. So these piecewise elastic splines are actually smoother and physically accurate, more so than the polynomial splines. And then if we think of extending this problem in 2D to try to do piecewise elastic surface interpolation, then we would use the 2D Willmore energy with some point constraints. And then we would also need the analog of the isometry constraint to the 2D case. And of course, one could think of doing applying an isometric constraint, but that would perhaps be too rigid, so you wouldn't get interesting surfaces out of this. But the next thing to do is to impose conformality. So you don't force isometry, but you allow only for similarity transformations, this scaling of the metric. Okay, so this is my problem, and I'd like to spend a little bit of time talking about what we know about this. So from the mathematical side of things, we know that arbitrary conformal emergence of given conformal structures exists. So this is a case when we're not actually caring about Willmore. When we do start looking at optimal emergence, then we know less things. So there are some theoretical examples, and there's also some actual surfaces that we know of that are constrained Willmore, but only in special cases. So one example of special case is these constrained Willmore tori near the global minimizer, so the Clifford torus. But generally, we don't know what these surfaces look like. So in this work, we sort of proved a condition for optimality, meaning that we can check whether a given surface is a constrained critical point or not. And of course, surface in this work means discrete surface, so meshes. And we also have an algorithm. So we have an algorithm for actually producing these surfaces, which exactly solves this Willmore optimization problem under the conformal constraint. And both energy and constraints are nonlinear. But of course, this algorithm is not limited to Willmore specifically, so it can handle other energies as well. Okay, so we're dealing with triangular meshes. We have vertices, edges, and faces, and we have the discrete emergence being defined as a piecewise linear map that assigns point positions to the vertices. And for an emergence, we also ask that every vertex star has to be embedded. And then we need a notion of discrete Willmore energy. So there are a few options here, but we actually can use any of them. But the one that we did use in the paper involves the total weighted sum of squared mean curvature vectors. So here you've got this L matrix, which is a standard Coulton Laplacian, and then you apply it to the vertex positions F, then you get the mean curvature normal. Then you weigh it by this Hodge star, inverse Hodge star matrix, which contains the vertex areas, the Voronoi vertex areas, and then you sum it all up with a trace. And this approximates the smooth definition of the integrated squared mean curvature. Okay, then we need a notion of discrete conformal equivalence. So for that, first we need a metric. So a metric is specified by positive edge lengths that we assign at every edge. And they need to satisfy the triangle inequality in each triangle. And this is what turns each sort of triangle, each face, into a Euclidean triangle. So then the notion of induced metric becomes that if we have a vertex to vertex position map F, the induced metric is the one that assigns as edge lengths to each edge exactly the distance between the corresponding vertex positions as they are described by F. Okay, so the conformal equivalence definition, we have two metrics, L and L tilde, and it should involve some kind of pointwise scaling of the metric by positive factors. And now again, there are a few options, but the one that actually ends up being the best one is the so-called CETM, which places the conformal factors at vertices. So what CETM says is that two metrics, meaning edge length assignments, L and L tilde, are conformally equivalent if there are numbers U per vertex such that the lengths L tilde are equal to L scaled by these by the average of these numbers U and at I and at J. And you also apply this exponential to make sure that the scaling is positive, because you always, of course, need positive edge length. So for example, if we put a conformal factor like these u's, if we set them to 0 everywhere except at the single vertex I, the conformal change that happens is that all lengths of all edges stay the same except those of the edges that are coming out of the vertex I. So those are all scaled by the same factor. And of course, a positive U means that we're expanding, we're making edge lengths bigger, and negative U implies that we're shrinking. Okay, so instead of trying to keep track of the scale factors at the vertices, an equivalent way to characterize whether two discrete metrics are conformally equivalent or not is by looking at the so-called length cross ratios. So for this sort of setup here with these two triangles, we have the length cross ratio, which is defined as a ratio of two products of length. So on the top, we have the lengths of the sort of opposite edges, IL and JK, the cross ones. And then at the bottom one, we have the other two cross ones. So LJ and LKI. So this is called the edge length cross ratio. And it, like the set of all edge length cross ratios, completely characterizes the conformal class. So if we keep the length cross ratios the same, then we are staying within the same conformal class. Okay, so this is a good condition to use because if we take the logarithm of these edge length cross ratios, then we get a linear relationship for this conformality. So if we replace the edge lengths L by their logarithms lambda, we can write the conformality condition as a condition involving a matrix, this E times E matrix C. And this encodes the combinatorics of the cross ratios. And then we can say that the space of conformal classes for a given discrete metric, it can be identified with the image of this matrix. So this is sort of brings us to the constraint optimization problem. So we can translate any variational problem involving this conformal constraint to a standard constraint optimization problem. So the energy here can be arbitrary. So it doesn't have to be Willmore. It can be surface area. It can be volume or anything else. And the way we deal with this constraint optimization problem is we look at it with Lagrange multipliers. So you just form this Lagrangian with this energy and the constraint, and you can sort of work the whole thing out and get the Euler-Lagrange equations for this problem. And yeah, by taking derivatives of this Lagrangian. So if we actually work this whole thing out, it brings us to perhaps what is the main theoretical contribution of this work, which is the condition for criticality of an arbitrary energy under this conformal constraint. So these conditions, they involve the gradients of E. So this is a vector at each vertex, essentially. It tells us what happens to this energy if we fix all the vertices except that's one I. And then what the optimality condition says is that a discrete surface is a constrained critical point of an energy E if and only if there are numbers per edge, which we call Q, such that two things hold. So the first thing is that the Q's outgoing from any vertex I sum to 0. And second, the gradient of E at any vertex is a linear combination of the outgoing edge vectors, which are weighted by these Q's. So these Q's are exactly the Lagrange multipliers of the constraint optimization problem that I mentioned in the previous slide. And in fact, these Q's, they can be perhaps understood via physics. So they have a physical interpretation. So if we think of the conformality constraint as describing some kind of material, then this will be a material that doesn't care about being scaled or shrunk as long as this scaling or shrinking is happening isotropically, so not along a single direction. And this imposes a condition on edges because the conformal condition was defined on top of an edge-based metric. So the Q's also live on edges and they multiply the edge vectors. So one can think of having a little spring on each edge that is sort of pushing or pulling according to the sign of the Q. And then you have the total push or pull being the sum of the Q's. So the first condition says that the total energy in shrinking this or stretching all the edges around the vertex simultaneously is 0. So at the optimal shape, the material doesn't care about isotropic scaling. And then the second condition says that at the optimal shape, there's an equilibrium of forces. So the edge forces Q that enforce this conformality have to counteract the gradient E force that wants to make the energy smaller. So maybe this is somewhat easier to see on the example on the right. So here we have a constrained minimal surface. So E here is the surface area. And what you can see perhaps is that the conformal forces, which are shown as these arrows here, they sum up to a net force that sort of pushes outwards of the cylinder. And this counteracts the area minimization force, which wants to squeeze the cylinder. So it points inwards along the inward mean curvature normal. And yeah, so this optimality condition essentially can tell us if we are at a critical point or not. So what it can tell us is how to actually get a surface. So we don't have, for that we need an algorithm. So we need to come up with a way to solve this constraint optimization problem. And perhaps the standard thing to do would be something like projected gradient descent. So what would happen here is we start from a given immersion, and then we look for an update direction for the vertex positions that would reduce the energy while also satisfying the constraints. So the problem is that because the conformal constraint is nonlinear, this PGD would also need to project the updated F back into the space of conformally equivalent immersions. And it would have to do this at every iteration. So this would mean that it can only take very small steps to make progress. So instead, what we did is use a very recent method called competitive gradient descent. So this was inspired actually by game theory. I'm missing a citation here. It came out, I think, in 2019. So, so the game that we're playing here is this minimax problem for the Lagrangian L that we saw a few slides before. So there is a minimax problem because we want to minimize this Lagrangian with respect to the primal variables f and maximize it with respect to the dual variables, the Lagrange multipliers q. So then we have this sort of game and we have one player who's only trying to minimize the energy, so minimize L with respect to F, and then the other one only cares about the constraints and tries to maximize L with respect to Q. And what happens in CGD, so is both players try to anticipate what the other player will do before they actually make their move, meaning compute their descent direction. And this boils down to writing bilinear local approximation for this Lagrangian in terms of F, the updates for F and Q, and solving for them simultaneously. So the good thing about CGD is that it doesn't have to stay within the constraint manifold throughout the optimization. So it only asks that constraints are satisfied at the end. And this is great in particular in situations where the projected Willmore or other energy gradient becomes nearly zero. So for example, in this region on the box there on the top, this is what's happening there. And as you can see, the PGD tends to get stuck there. So it doesn't make any progress. But instead, what CGD can do is sort of step out of the constraint manifold for a while. And you can see this at the bottom. So the spike in the blue curve there means that the CGD decided to violate the conformal condition for a little while. And this, if you look back on the top, it enabled it to reach lower Willmore values. Okay, so this was generally it. So CGD will work quite well on meshes and vertex positions. What we did find is that it's sometimes better to work with a differential surface representation. So far, I've been talking about using F as the variables in the constraint optimization algorithm, but we could think of instead not use the vertex positions, but use the edge vectors as variables, so candidate edge vectors. So for a mesh, they would have to close up in each triangle because they would have to form a triangle. And what this means is that you're representing your mesh via affine transformations that map every planar triangle to some 3D configuration. So this is called triangle field in the paper, but is actually in the same spirit as other differential representations used in geometry processing. So the triangle field, of course, it doesn't have to stitch up to a surface. So if it does come from an F, then it will. But in general, this won't be the case. And what this means is we need to add a constraint for integrability, which we can add easily to our CGD solver. And yeah, so the whole reformulation, the whole problem needs to be reformulated in order to work with this differential representation. So this is all in the paper. And in fact, one can rewrite the entire optimality conditions and everything with this representation. And it ended up being an interesting thing to do because a lot of surface theory turned out to be possible to rewrite with this sort of candidate differentials of surfaces. And in fact, one can come up with discrete and smooth theories that are to a certain extent compatible with each other if you use this differential representation. So right, so the practical advantage of using this differential representation is that we don't need to have an initial immersion to start from when we're trying to do some kind of Willmore or other flow. So we only need a discrete metric without having the specific vertex positions. And this can be useful, for example, in cases where we don't have an initial surface. So for example, one might want to use this Willmore to do some hole filling for a surface, and there we don't have initial vertex position. So we might just want to start from a generic triangulation and let the algorithm do the rest. And also in another work, the one I'm showing here on the right, there the focus was on reconstructing immersions from metric. So there also there was no available starting immersion. And we can think of this work as sort of an extension of that work. So Albert is here actually, I think, in the audience. So yeah, there the focus was on isometric transformations, and here we're working with conformal ones. So yeah, isometric transformations being a subset of the conformal ones, of course. So there are cases where where not having to start from vertex positions are useful. This is my point here. In our sort of context, the ability to actually make surfaces without starting from a surface is useful when we're trying to visualize abstract conformal classes as surfaces. So for example, I talked about before having these special cases where constrained Willmore surfaces are known, for example, for tori around the global minimizer, the Clifford torus. So if we were trying to do this here, we would actually not have, because we don't know what the surfaces look like, we don't have an immersion to start from. And for a torus, the conformal class is determined by the shape of the fundamental domain of the torus. So this is this parallelogram where on the plane where we need to glue the sides, the opposite sides in the right way to get the topology of the torus. And if we have two tori that are not conformally equivalent, then those will come from parallelograms that have different aspect ratios or skewness. Yeah, so here you can see an example of starting from nothing. So starting just from a triangulation of the parallelogram, and then you do this Willmore flow to land to the final constrained Willmore torus. And what you can also see is that during the iterations, you don't yet get something that stitches out to a surface. And this is because the competitive gradient descent only satisfies the integrability constraint at the end of the optimization. So using this whole triangle field and algorithm, so we can actually recover the known special cases of constrained Willmore tori that were known before in this sort of special case near the Clifford torus. But we can also visualize a constrained Willmore tori of any general conformal type, which was not previously possible. And so for mathematical visualization, this might be useful. So you can see abstract conformal types as surfaces. And one thing to mention is that this is a case where theoretical optimality conditions are useful because since exactly there are no known results about how big the Willmore value is at a general case of constrained Willmore torus, then we don't have a way to know that we're at a minimum. But our optimality conditions exactly allows us to do that because we can check if it's satisfied to, let's say, numerical precision. Okay, in the spirit of elastic splines, we also can do point constraints. So we already saw that the conformality constraint avoids getting two sphere-like results. So it lets us stay faithful to the input geometry. when we're using the Willmore energy as for modeling. And this can maybe be seen more easily in a toy example where we're doing this Willmore-based modeling starting from a sphere topology, and we're trying to do that with 4-point constraints. So if we don't add conformality, no matter where we move these points, we will always get back around sphere as a minimizer because 4 points always lie on the sphere. But if we add the conformality, then just by moving 1 point, then there is no conformal transformation that will take us from the old positions to the new positions. So we need to get something more interesting, and that makes the shape deviate from the round sphere. And so in general, if we try to do Willmore minimization with point constraints, constraint Willmore minimization, then what we get is as spherical as possible interpolates of the points. And this has been used before because it's desirable for architectural geometry, and I think Amir can back me up on this. So in this work, there was a subdivision scheme that was based on Möbius geometry, and we can do similar things with our sphere preserving interpolants. So, right. So this slide shows how the intrinsic conformal geometry actually affects the extrinsic shape of the surface, which is an interesting thing to study. So for example, for tori or cylinders, in both these cases, the conformal type is described by these two shape parameters of the fundamental parallelogram, meaning the aspect ratio and the angle. And what we can see here is that surfaces become more twisted as we increase the angle of the parallelogram. While if we change the aspect ratio, we get thinner or thicker handles for the 3D shape. The other thing about this conformal twist is that it controls the amount of bubbling. So generally, plain Willmore would like to do very spherical shapes, but if we add this, this conformal twist, we can control the bubbling. And as I said, we can apply this whole pipeline to other energies, so not Willmore. And one classical example is the area energy. So the minimizers of this model the behavior of soap films. So these are the minimal surface, and they often collapse. So because area makes material shrink, this sort of tends to happen. But if we add the conformality constraint, you get the constrained minimal surfaces. And this is corresponding to a material that can shrink arbitrarily, but only in an isotropic fashion. So this makes for surfaces that look very different than classical minimal surfaces. And in particular, as you see here, they don't collapse. And in general, this conformality condition is the right way to model the so-called isotropic oxiding materials. So these are materials with negative Poisson ratios, meaning that if one stretches them along a direction, they also become thicker perpendicularly to this direction, and they do that isotropically, so no shearing. And one can easily make objects that behave this way. So one can take, for example, a sheet of some copper or aluminum or some other inextensible material and cut it in regular patterns and then pull it. So what will happen then is that the sheet would expand in both directions isotropically. And there is prior work where these materials have been used for fabrication and architectural modeling. So that's something that we actually want to look into more in future work. Yeah, so we already saw that different amounts of like different parallelograms make for different twists in the 3D immersed tori. So what this slide shows is that there's sort of other interesting things you can do with the conformal constraint if you also add boundaries. So here you see on the left that the cylinders, which are also controlled by the fundamental parallelogram, and they tend to exhibit similar twists if you change the domain as a tori. And then on the right, we can prescribe boundary conditions and keep the edge length cross ratios the same. And that also gives interesting surfaces with twists. Right, the other thing is that conformal constraint also preserves the meshing quality. So in fact, whatever properties the triangulation has in the initial surface, it will stay so in the output surface. So we also are insensitive generally to triangulation. So here, what you see are two different triangulations of the same shape on the top right. And in both cases, you get the same shape in the minimizers. Another thing here to mention is that we are using a completely discrete notion, the CETM of conformal equivalence. So this is in contrast to other methods like Crane et al. 2013, where a discretized version of conformality was used. So there one was trying to get to conformal equivalence by approximately discretizing smooth conformal deformations in some kind of piecewise linear fashion. And what we found is that it turns out that this tends to accumulate numerical error, and this means conformal drift, especially in the case of this tori with like a lot of twists present, very non-square fundamental domains. And this is what this slide is showing. So it's showing the quasi-conformal error for these two methods. And you can see that our method doesn't have this issue of conformal drift. So you can preserve the conformal class exactly, and you can verify it with optimality conditions. So also we can of course do any genus of surface. So these are the first high genus constraint Willmore surfaces that have been visualized. And it's also interesting to note that one can use Willmore also for surface fairing if one adds this conformal constraint, because the conformal constraint will lead, it can preserve textures throughout the fairing. So this is sort of shown on the right here. So what we do here is we change the energy that we're optimizing so that it balances between Willmore and some kind of closeness to an initial immersion F0. And this is sort of in the spirit of energies used in the gradient domain denoising for images or surfaces. And there are, of course, more results in the paper, also the proofs for the optimality conditions in both the case where we're using vertex positions and in the case where we're using triangle fields. Okay, so this was mostly my talk. So I've been talking to you about the problem of finding discrete surfaces that are the critical points of the so-called Willmore energy, but also other energies. And we have been using the CETM notion for discrete conformality. So yeah, we looked at the theoretical optimality conditions that you can derive from the Lagrange multiplier approach to the constraint optimization problem, and you can use them to check if you're at a critical point. And we also look at an algorithm, so based on the competitive gradient descent method, and exactly solves this nonlinear problem, nonlinear constraint problem of Willmore variational conformal constraint problems in general. And we saw some interesting shapes that you can get through this pipeline, which we think might be interesting for investigating more to make them useful for applications. And so another thing that is very interesting for us is to investigate connections between the discrete theory that we developed in this work and what we know from the smooth case. So for example, the Lagrange multipliers, these Q values that we ended up having in this problem, they turn out to be exactly the DDG, the discrete differential geometry counterparts of the so-called holomorphic quadratic differentials, which is the Lagrange multipliers that appear in conformally constrained variational problems in the smooth case. So that's sort of an interesting connection there, which we would like to study a bit more. We could also, of course, try to investigate what we can do with the competitive gradient descent in other settings, so other optimization problems with other energies. And we would also want to investigate how we can use the conformal constraints in a design or form finding scenario. So for example, we could think of trying to prescribe twists on a surface or even the conformal factors U directly and do some modeling or form finding. Okay, so that is my talk, and thank you very much. And I look forward to your questions.
Thanks, Olga, for the excellent talk. We have some time for questions. If somebody wants to ask, just feel free to unmute yourself and ask. Maybe I can start. So I was wondering, you have this, like this is the generalization of shape from metric to conformal maps, right? So can you do this? Can you do conformal shape interpolation with that? I can interpolate the metric between two shapes and then generate the conformal embedding.
Quite possibly. I don't think this is something that we did, but I mean, the way you described it, it sounds possible. I don't see why not. You mean like you interpolate a metric and you come up with some conformally equivalent shape?
Exactly. So you interpolate the metric squared, like this edge length squared. This is something
Right.
we did in the planar domain, and then you generate the conformal map. Yeah, it should be interesting.
Right. Yeah, we never tried this, but that's that would make a nice, nice result. But I don't see that.
But I mean, are you like there are multiple embeddings, right? So do you have to add constraints, or which solution would you get to a specific selection of edge lengths?
I mean, whatever the optimal thing, the optimal Willmore, like you would have to add some kind of energy that guides you, I guess. And in terms of like, if there are multiple minima, which there might be, I don't know which one it would do, but yeah, I imagine that there would be some energy that tells you, or maybe some energy like the one for fairing, where you sort of try to stay close to the inputs.
Yeah, exactly.
Something like that. Yeah, that would be my first attempt, I guess.
Okay, cool. Maybe follow-up work. Anybody else? Great renderings, by the way. I was like,
well, that goes to Yusuf, who is not here, but yeah.
I was awed by your renderings.
Blender, sorry, Houdini magic.
Yeah.
Thank you.
Any more questions to Olga? Or Albert, if he's still awake?
I don't know, surprisingly so. Hello.
Yeah, I'm still here.
Yeah, we have the whole, this is in SIGGRAPH, right?
Yeah.
Yeah.
So we have a pre-SIGGRAPH screening.
Yeah.
Yeah. Okay, well, anyway, if there are no further questions, thanks again, Olga. It was great to see you virtually.
Yeah, absolutely.
Hopefully at some point we see you for real.
I know. Well, virtual SIGGRAPH for sure, but yeah.
Yeah. Okay, thanks everyone. And we'll have another seminar in 2 weeks from now. Bye.
Bye.
Bye.